Hello, everyone, and welcome to our community call on May 5th. And we're talking about Qrng today. Here with me is Burak and from API 3 and Dr. Aaron Tranter from ANU. If you guys would like to introduce yourselves briefly.
Sure. As Rachel mentioned, my name is Aaron. So I'm actually part of the quantum optics group at the Australian National University. So we do a lot of atom-light interaction, we do quantum information, anything really that has to do with quantum computation and communication. So we developed the Qrng probably about 10 years ago now, and have been running it as a sort of community service, and have recently made the push to bring it to a more reliable and user-friendly service.
Great. And Burak?
Yes, I'm Burak from the core technical team. And then I also work personally a bit on the integration of a node with AQN. So that's why I'm on the call.
Awesome. Yeah. And like I said earlier, we're here to talk about API 3 Qrng. It's the newly announced kind of thing that we've got here going on. What exactly is Qrng is probably a lot of people's first question. So Dr. Tranter, can you kind of briefly talk about the quantum aspect of what goes on?
Sure. Yeah, so basically Qrng obviously stands for Quantum Random Number Generator. So the way it works is you have, when you think about vacuum, right? Vacuum is basically the absence of stuff. We have this sort of idea that when you consider a vacuum, that it's sort of empty, and that's what classical physics tells you, right? So space is empty; it's got nothing in it, maybe a particle or two whizzing by, but really it should be empty. But actually, when you start looking at things in quantum mechanics, it actually says that that this vacuum is not empty. It actually contains something called virtual particles, which discontinually pop in and out of existence, right? And that's a consequence of quantum field theory and a bunch of other complicated maths and quantum mechanics. But basically, that can be actually really useful. So these vacuum fluctuations are actually intrinsically random. So they are actually guaranteed by quantum mechanics to be completely random, because if they're not random, that comes with a lot of problems and would pretty well break our material world. So we can actually do this nice thing where we measure these fluctuations. So the system that we run is actually what's called a coherent measurement. So it's basically using a bright field, a laser, to measure these vacuum fluctuations. So you can take these fluctuations, put it on something that's called a beam splitter, and just straight up measure this noise. You take that noise, which is fundamentally random, you can then hash that into a bunch of random numbers, and then push that to some API or some cloud service, which in this case is where we send it, either through AirNode or through the AWS implementation of the API. But yeah, I mean, that's fundamentally how it works. There's a bit of, complicated physics that I've sort of swept under the rug there, but that is the basic outline of how it works.
I figured there was some highly complicated math stuff happening under the hood to make this happen. I'm assuming it's like a big device in a lab somewhere as well. Can you talk about like what the device itself actually kind of looks like?
Yeah, sure. I mean, it's actually not that big, surprisingly. It's in our labs, but it basically comprises of a fiber laser, And the reason you use a fiber laser is just it's nice to be able to contain it. And then a bunch of fiber optics. So you can actually do all your beam splitter operations with fiber, which means you don't have to send your laser around the lab. So basically you don't have access to the laser while it's traveling. And the only other thing you need is just some detectors and some fast electronics. So we have a thing called an Fpga, which is a field programmable gate array, which is basically reconfigurable logic. And all that serves to do is basically take the measurements that you make from your detector, turn that into things that are actually numbers, because really what you're actually measuring is voltages, right? So you need to do a bunch of fancy demodulation, and then actually flattening out that distribution to make it to make it actually useful, right? So it maps to something like an 8-bit integer. But the whole device footprint is probably only on the order of maybe half a meter square.
That's actually really interesting, because like the stuff that I've seen that deals with kind of quantum stuff before, I always imagine it like takes up a whole room or something like that, and it's like this massive thing. It's funny because it's like such a small thing that you're measuring, literally particles, but the device is huge, right? So I think that's kind of interesting.
Yeah, so for a lot of the general quantum technology, noise is a big issue, right? Because you're having to isolate your system from the environment. So that is the big problem with quantum technology, is it just couples to literally everything. So if you want to do anything that's useful, so sensing or computation-wise, you have to isolate it, because otherwise it'll couple and then it'll just decohere, which is not very useful, because decoherence is just straight up loss of information, right? Then it's just a classical computer or a classical device, and that's not useful at all, right? Or it's as useful as a classical device, which is not what it's supposed to do. But for the Qrng, because you actually care about measuring the noise, and you're doing coherent detection, which is what they call a bright field type measurement. You don't have to cool it down. You don't have to isolate it from the environment. In fact, you're just measuring fluctuations within a certain band. So noise that's coming from the environment, such as acoustic noise, that kind of stuff, it's just not in the bandwidth of the measurement, so you don't have to care about it.
Very interesting. That is super cool, actually. And you guys have run this for quite a while, right? This is an established project.
Yeah, so we initially created this about 10 years ago, which is actually slightly before my time, before my PhD time. And that was like sort of the first iteration of this project. And that was just sort of a curiosity. I mean, one of the things that we cared about using it for at the time was actually for things like picking measurement bases. So you do this interesting thing in quantum communication where if you care about, for example, constructing a key, or doing fundamental tests of reality, you actually need to pick how you measure randomly. So if you want to remove all sources of bias, you need a fundamentally random source, something that you can actually point to and say, all right, there's no loopholes here. This source is not, biased by anything. And so that was one of the things that we just needed to do, was sort of a curiosity. And then we thought, oh, well, you know what, we could actually just provide this as a service for people to use. If they want some random numbers, they can log on. And so the old site, we had a lot of cute little demonstrations where it would, take these numbers and then turn it into random colors, random sounds, or these kind of things. But now, actually, we've sort of moved a little bit away from that and found that people are more interested in it being reliable and having redundancies and less about whether it can make pretty music.
But it's still cool. It's like, something that I think people that are developing stuff on the blockchain want sometimes is the pretty colors or the random sounds, especially with something like generative NFTs or something like that. So there's definitely an application for that data still being used. And speaking of the data being used, Burak, how is API 3 providing access to this? How does it connect up to what we're doing?
So this wasn't within our plans for a long while. Like if you look at our white paper, there's nothing about random number generation or serving them, even though like that is a part of the bread and butter of Oracle projects for a while. But then our approach to things is essentially using first-party oracles, meaning that we have the data source also operate the Oracle node, so that essentially the supply chain of data is not broken. So the data source pushes it to the chain, and then once it's on the chain, it cannot be tampered with anyway. So this essentially results in the most reliable way of delivering data to the chain. But then if you think about random number generation, like who owns random numbers here, essentially, everyone is drawing from an infinite bag, and then nobody owns it actually. So initially what we thought was that like there's not really a distinction between random numbers. But if you think about the Oracle problem in general, the main problem here is that providing an Oracle service is arbitrarily easy. Like I could today set up an AIR node to deliver random numbers in less than half an hour, and it would work very well, like it would be very reliable. But then the main problem here is trust, essentially. How would anyone be able to trust me? They cannot. And then decentralizing this has absolutely no use, because like if you have a decentralized random number generation built out of multiple untrustworthy people, the results will again be untrustworthy. So essentially, the problem of oracles is somehow you need to be able to rely on pre-built trust. And then with random numbers, it wasn't clear how this could be done. So AQN is essentially turned out to be a very good solution in this regard. One, because like the way of random number generation is one, very reliable, but then also nice, and I think about Qrng is that it is not trivial as like pseudo random number generation, and that this provides some kind of like a Sybil attack guarantee in that now the people who can provide the service are very limited in number, and then they are like in all cases established organizations, either universities or businesses or whatever. So both on their own and in decentralized form, like Qrng seems to be almost the ideal way of providing random numbers to on-chain use cases. And then, yeah, the nice thing about AQN is that they approach this from an API provider angle, which is unique as far as I can tell in the quantum random generation space as a whole, because there are some services, but they are not as easily, publicly accessible, permissionlessly accessible as AQN. Because, for example, if you look at AWS Marketplace, it is listed there, and then it is vetted by the AWS solution architects, and then it is very reliable. It doesn't rely on, for example, obscurity. For example, one thing that some API providers do is their thing is not publicly available, so they can assume it will not, suffer too much stress from incoming requests. While when you provide this as a public service, now you have to make it very redundant, very reliable, which we have seen that AQN has achieved. So this is also good in that, well, in smart contract use cases, you want random numbers, you want to create pictures and colors out of that, but you also want that to be very reliable. So that's also very important, which is what we could achieve here. But then the nice thing about all this was that the actual integration is pretty much the same thing that we do with all API providers. We just integrated an API provider through AirNode to blockchains, and our job was done. So this was also like a very low effort integration from our end, but then it created a huge amount of value, or we will see that it will create a huge amount of value.
And that's something that, like, I think, yeah, it has like greater application beyond just the colors and the sounds and stuff like that. People could use this for stuff that's quite serious, and they would need the security and they would need the trust. So, you kind of have that reliability trust there, and then you have the trust of the university itself, and then like from a device kind of standpoint, it's probably in a very secure lab, so it's a pretty rock solid thing, and you're definitely getting random numbers from it, because it's not like an algorithm generating something which could produce non-random numbers. It's like you're measuring particle movements, which are inherently random. Otherwise, physics just breaks, right?
Yeah, I mean, that's the thing is, when we were running the old version, we would often publish statistics, and we intend to do that with the new service as well, because you can just publish a big block of numbers and say, go run your tests. Like, we've run these tests. Here's the results for us. You can verify that these numbers are random by whatever test you want. Run die hard, run a machine learning code, run whatever you want. If it's not random, it'll show up. And the sort of it's in our best interest to keep them random, because we also want to use it. It's no good to us if it's not random, because that then that makes problems for us as well.
Yeah, we were talking about it a little bit. Kind of, this was like the origin of the quantum number thing was like something that you guys personally want to use yourself for various other kind of quantum and physics experiments in your lab as well. So you guys have a personal interest in making sure it works the way that it should work every time. So that's pretty cool.
Yeah, no, for sure. I mean, it's a very nice resource to have. One of the things that we saw for people that were using it was coming out of research institutions, right? And I think that's a big selling point for them, is to be able to point to this source of entropy and say, well, this is not a problem in my research. It's not a problem in my my logic. It's not a problem in my decision making. This is just a thing that is guaranteed to be random. And so now I don't have to worry about that. Now I can actually look at the results that came out of whatever research I happen to be doing. I don't have to talk about was this truly random? Like, here's a bunch of papers that show you it's truly random. Like, we had research collaborations where we invited people to basically come and break it. Come and tell us if it is random. Independent universities of like, here's a bunch of data, run your tests, and let's see if it is actually random. I think the most recent one was with University in Melbourne, and they got a neural network to basically try and predict ahead of time whether what number might be coming up, and it was doing no better than random chance, and basically showed through all of the die-hard tests as well that it was still random. So
that's pretty cool. Like, you guys have actually, I mean, like I said, you have a personal interest in making sure it works for your experiments, and as scientists, you're always trying to kind of say things that might have affected the outcome of your experiment, right? And to be able to look at this and say, hey, here's however many papers that say this is definitely a random number. That's pretty cool, for sure. Especially having other universities invited, hey, come break our thing. Like, that's actually pretty funny.
Yeah, it's an amusing paper to write. It's like,
right.
I tried to go break this thing. I didn't break it. Anyway, here's the results.
I didn't break it. Hey, it works. Here's the result. It works, right?
Yeah,
so
pretty much.
From like a blockchain side, Burak, can you kind of think of any kind of applications that this API Qrng thing might be useful for?
Mm-hmm. Yeah, it is. I was actually thinking about this when I'm thinking about like actually useful and exciting use cases. I'm always thinking about what happens in the real world, like a part of the real economy, but it being done through smart contracts, and then some kind of additional value being created by that. And then in our day-to-day business processes, what do we want to happen at random is a pretty interesting problem, because in almost all cases, if this is something, if it's something financial, we almost never want it to be random. But then when something is related to humans, then we want it to be random. So some examples that I can come up with is, for example, miners choose transactions and then put them in an order and then create a block out of it. And then they try to mine that block. Once that block is mined, it's added to the blockchain, and then you select the next block, whatever. And then the problem is this approach is that the miners can manipulate the ordering of the transactions to get some kind of value out of it, which is called MEV. So, for example, we would actually want this to be random rather than human selected. So this is where the human factor comes in. Another thing that I can think of is this happens in subject workable use cases or governance use cases, where you have, let's say, 100 people that can make a decision, but you don't want all of them to do it because it will take a lot of their collective time, and it will cost a lot of gas for all of them. So you want 10 of these 100 people to, essentially it's a jury duty. And then you want that selection to be done randomly, but if you have someone select the people that will show up in a jury, then there is an obvious, incentive to select in some biased way, which is why you would do that. So for example, this is another use case where you would use random numbers, and it is not just, a gambling use case, but it's actually creating some kind of, benefit. And then you also have the gambling use cases. And then, I'm also thinking of a lot of the NFT use cases, which are not, at least they don't appear to be gambling, but then even if you're doing something financial, if it's speculative in nature, it is almost like gambling. So, for example, I like modeling things in the same way so that I know how to treat them. So for example, a lot of the business cases can be modeled as a prediction market. And then a lot of services can be modeled as an oracle. And then a lot of business use cases can be modeled as gambling, even though it is not the kind of gambling that you think about. So this is an obvious case where you would want to use, safe RNG.
I think it's kind of crazy thinking about quantum jury duty. Like it's a real world application that's definitely you want this to be random, right? But can you imagine the quantumly generated jury duty list? That's actually pretty cool. It's a real life use case, like you said. It's something that you're gonna want randomness for. But to think that it might be done by quantum mechanics someday is actually kind of cool for me because I love this kind of stuff. But quantum jury duty, that's a new one.
Can I ask one question to Aaron? So I was thinking, what additional quantum computing Oracle services could exist? For example, if I could have the inverse of a hash computed for me on chain, that would be worth a lot. So is there stuff like this that is not obvious to people like us, but actually this may be a good idea to integrate to a smart contract?
Possibly. So we're sort of really just scratching the surface at the moment of what quantum computation is actually going to bring to the table, right? There's a lot of speculation about what problems it'll be able to solve well. And some problems, they've demonstrated there is an exponential speed up. So factorization of primes is the big one, which is why people get scared about, encryption breaking with quantum computers when they actually become useful. I guess the good news is that that scales really poorly. So you actually need quite a large quantum computer before you actually get speed ups that surpass classical superclusters, right? But yeah, I sort of always thought that the way quantum computing ends up going is, it's not going to be people owning their own quantum computer because there's just no need for that. But it'll be like an enterprise type service. So if you want something computed for you, then you would farm that out, right? Almost like a cloud-based service. So, maybe you're a company and you have distribution problems, right? The classic traveling salesman type problem where you need to distribute workers to go do a particular thing, whether it's delivering packages, actually just getting resources from point A to point B, all of that kind of stuff, right? Then you could basically farm that out to systems that are, sort of publicly available, or have some sort of Oracle thing, and you could actually have them compute them and then agree on whether they what the right answer is, because some of them will be approximate, some of them will be exact. It depends on the problem. Quantum sensing is another big thing that's supposed to sort of bring almost a different revolution, right? So quantum computation promises faster computers, but sensing promises things like, being able to, the sort of accuracies that they quote is like, if you throw a gravimeter on a satellite, then you can sense the presence of a blue whale, right, in the ocean somewhere, which is a stupid measurement to be able to make, like, stupid accuracy, I should say. But, those are the kind of things. So then you could have these distributed quantum sensors that are actually making measurements on things where you're like, oh, okay, now I have this distributed network of sensors. Do they all agree on this particular thing? And, because of the way you can set them up, you can make them to be tamper-proof and, all that kind of interesting stuff. So there's certainly lots of opportunities for these kinds of technology to be integrated in a decentralized sense, I think.
That's really cool. Like the entire time I'm thinking about all this stuff, all I can think, and it sounds very like generalistic. That's really cool. That's really cool. But it is. It's like the new stuff, and the fact that there's other technologies that you guys are working on and other researchers that are working on that their data might be available on chain someday too is cool, for lack of a better word, essentially. And like the QRNG, API 3's Qrng, it's available on quite a lot of chains right now, as far as I know. Burak, you got any comments on the availability of this if you're a developer and you're listening right now, and you want to integrate this into your project?
Should I list them?
You can list them if you like. Yeah.
Yeah, so it is like not even on the list. We are also providing it on for the 4 Ethereum testnets, Robson, Rinkaby, Gurley, Cohen, which is quite nice. But we're not even counting them when we were saying 13. It's actually 17. So we have it on Arbitrum, Avalanche, BNB chain, Ethereum, Phantom, Gnosis chain, Metis, Milkomeda, Moonbeam, Moonriver, Optimism, Polygon, and RSK. So this is pretty impressive because, as far as I know, like there has never been a kind of an Oracle service that is on so many chains. Simply because like it is quite difficult to, like, what you would have to do is you would have to run 13 nodes, one for each of these chains. And then you would have to maintain them separately. You would need to operate them separately. You would need to pay for them separately. So this is essentially why people don't do this. And a few of these chains are very established. A few of these chains are very new. And essentially not much is being built on top of them. And then this has been one of the problems that the whole space has been facing nowadays is, well, Ethereum is too expensive. You can't build on it. And then there are a bunch of these smaller chains, but there's nothing on them. Like there are no services on them that you can build on. And then no one builds on them. And then they continue building on Ethereum instead. And then it becomes more expensive. More chains pop up that nobody uses, and then like this just goes on and on. But if you could provide Oracle services on all these chains, then like that would have been largely solved as a problem. But then, well, you can't really have Oracle node operators, especially API providers, operate these many Oracle nodes. And then we essentially designed AirNode exactly based on this premise that, okay, the API providers need to be operating this thing. So like it shouldn't require any kind of operation. It should be just deployed and work, and it shouldn't even need to be monitored. It isn't, because it largely depends on managed services. But then also, a single node deployment serves all of these chains, and then it serves all of them in an isolated way. In that, so for example, we are serving it on 4 Ethereum testnets. So spam the thing all you want on those testnets. You will not be able to affect the mainnet that it's serving on, which is why, like, we essentially treat all chains in an isolated way, and then we are reserving concurrency slots so that some chain cannot eat up the concurrency slots of another, etc. So a lot of cloud infrastructure kind of considerations were made around this so that it is actually very reliable. And then, the other thing is people really don't want to serve this many chains, because generally how Oracle nodes work is you make a request and the Oracle needs to respond with a transaction, and then transactions cost gas. So what an Oracle provider would have to do is they would have to buy the native currency of all these 13 chains. They would have to fund their wallet that it's going to make the transactions to do the fulfillments. And then they would need to price their service in a way that this is profitable. And this is, like, pretty intractable as a problem, because like the price of the native currency changes, the gas cost of making transactions change because the chain is more or less congested. And then you essentially, Oracle service, you first need additional Oracle services on the chain, and that like you need to have a price feed on the chain, and then you need to have a gas cost feed on the chain as an Oracle service, so that you can on the fly calculate, okay, how much should I charge my user, and then you do the calculation, you charge them that. And then this essentially means that, essentially nobody wants to serve the chains, like go into all this effort because the chain is not being used yet. And then this creates this chicken and egg problem, because like the oracles are not there, so people don't build there. Because people don't build there, oracles don't come there. So how we solve that problem is that the AirNode protocol is designed in a way that the requester provides the funds for, like, they make the request, so they pay for gas for that, but they also pay for the gas of the fulfillment. And then this essentially means that if you want to serve an API on a new chain, you just deploy the AirNode, you point it towards that chain, and then like you don't need to care about the currency or like the funding of it, because the user will be essentially bringing their own gas with them. And then you don't need to worry about if it is profitable or not, because it doesn't cost you anything anyway. So in addition to this, you can add additional monetization schemes, such as like you can respond to only whitelisted addresses, but then essentially model this whole service as a kind of a more traditional API subscription, rather than like you can isolate or decouple all of that pricing considerations from the blockchain realities of gas costs and network congestion, which makes the problem a lot more difficult. So this is essentially how we were able to do this with AirNode with so many chains, and we are planning to do it for more. Is that the whole solution was built to be able to achieve this.
And it's free to access, right? The API 3 Qrng is like free. Like we're providing it. We're not just charging people extra or anything like that for it. It's just there. Get the numbers. Get your quantum numbers, right? Speaking of that, we've got some questions from the community. And speaking of the quantum numbers, when a DApp requests a random number, how quickly can they expect to get a response from Qrng? Either Aaron or Burak, would you like to answer that?
This is very specific to blockchain, so I probably should. So the thing with random number generation on chain is that this depends on essentially the main vulnerability around random number generation is that you can request a random number, and then if you're able to request another one, if you don't like the first one, then even though the numbers are random, like the end result is biased, because you can just retry until you get the number you want. And then the problem at blockchains is that the blockchain transaction orders only are finalized after a few blocks are mined after the transaction is made. So this effectively means that the older a random number generation request is, the more secure its response will be, which is why random number generation Oracle services do not want to respond as soon as they see the request. And like this is a fundamental thing that this cannot be solved by Qrng or like whatever thing that you can think about. As long as the underlying blockchain structure is the same, this is an unsolvable problem. Like you have to wait until like some blocks are mined, and then after that you will have to respond. So essentially the response time is largely limited by, or not limited by, or inflated fixed amount by the AirNode waiting until, being sure that, okay, the transaction order is now fixed, so I can respond to it. So if they go to the Qrng docs, they can see what are the minimum confirmations for each chain. This means that on that chain, AirNode will wait until that many blocks are confirmed before responding. And then like this is the user-friendly way of doing things, because well, a lot of users will not be aware of this context, and if you allow them to set it, they will set it to 0 blocks. Like they will just want to answer right away, which is not the right way of doing things. So this is why this has been like decided for the user. But in following iterations, we may allow the user to specify the exact number of blocks that they want to wait for. But we may still like cap it at a level so that they can't ask for a too fast response, because like that would be detrimental for them too.
That's actually interesting. I would have thought like, oh yeah, it's good to get it as fast as possible, but there's actually like a mechanic to waiting is kind of good for this kind of thing, which is interesting. Another one that somebody asked was, can you get multiple random numbers in a single request? And if so, how many? I don't know if that's an Aaron question or a Burak question there.
I'll throw that one to Burak.
Okay, it's a Burak question.
Which one is that? Like
can I get multiple random numbers in a single request? And if so, how many?
Yeah, so the thing is, the Oracle responds to the transaction, which delivers you to random numbers, but then allows you to do anything with them. And then we can be quite flexible with this, because like as I explained earlier, the protocol is built in a way that you are paying for the gas anyway, so we don't care what you do with the random numbers. You can run an infinite loop if you want. Like it's your gas you're wasting. So essentially the answer to the question is, like you can get, the API returns a maximum of 1024 numbers. But the problem is, if you want to, for example, write all of that to blockchain storage, you will run out of gas. Like I'm not sure, but like it would have to be a single transaction filling all the block essentially. Like and then it would probably cost you, thousands of dollars, probably a lot more. So essentially, you are limited by what you want to do with the numbers. So if you want to write them to storage, I guess like you could do 10 easily. If you just want to emit them as an event, you could do a lot more. You could probably do 100 easily. So yeah, essentially there are two endpoints. One returns you a single number, the other returns you a number array whose length you can specify. But yeah, it's difficult to say anything without seeing the exact contract.
Okay. Yeah, makes sense. Let's see. Another question we have is, if you take the average selection of quantum random numbers, will the average still be random?
No.
No. Okay.
Because if you think about what the operation that you're doing there, so if you're measuring a distribution, let's say it's from 0 to 255, I expect to find every number with equal probability. So when I'm taking the average of a set of numbers, I'm basically asking what is the middle value, right? Middle is not quite true. Middle is median, but mean is close enough, right? In this case, for a sufficiently large distribution, you're asking what the middle is. And if I have enough numbers, my middle will always be the same. It'll just be the middle of those two endpoints. So then it's no longer random if you do that, right? Each individual sample is random, but you're asking a question about the distribution. And if you ask a question about the distribution, that has a fixed answer, which is not random.
Makes sense. It's interesting. Also, from the same person, and I think you kind of answered it a little bit. With Qrng, can I ask for random numbers and specify an arrangement such as a random percentage from 0 to 100, or would I have to find a normalization factor?
So Burak can probably speak to the Airnode implementation.
Mm-hmm.
With the standard API, you can specify the data type that it returns. So you can get an 8-bit integer or you can get a hex, and then converting that into a percentage is fairly trivial.
Mm-hmm. Like you would just apply a modulus operation on the unsigned integer. So I'm assuming that you're asking for a number between 0 and 100 with like arbitrary decimal points. So yeah, you would want to just apply a modulus operation on a single random number, and then you would get a percentage value essentially.
Okay, so it's definitely possible to say, like, I want a random number between X and Y. Give me a random number there, and you can do that essentially.
Can I ask you a similar question? Out of curiosity. So these random numbers are uniformly distributed. So like, are all things that are random in, quantum mechanics, are they all uniformly distributed, or do you do something, do you apply some kind of processing to achieve uniform distribution?
No, yeah. So actually, when we do the measurement, it's not initially uniformly distributed. We actually have a hashing operation to then make them uniformly distributed. You can assume that if your input to the hash is perfectly random, then your output should still be random, but just in a different shape, right? With the with things in quantum mechanics in general, you often don't expect to find a uniform distribution. Gaussian is far more common. You often find a Gaussian distribution. Depending on what you're measuring, you can get different statistics. So, for example, photon counting is Pearsonian or sub-Pearsonian or even super-Pearsonian, depending on what regime you're operating in. So, yeah, it's a very rich tapestry of what you might measure.
And then when you apply the hash function, like, doesn't that deserve the random, or like, aren't you making some assumptions about the uniformity of that or the output of that?
The uniformity of the hash function?
Yeah.
You are to some degree, but I mean, because your hash function is known, you can show, like, if I'm taking, chunks from this distribution and then putting it through these particular mathematical operations, I know what's going to come out on the other side, right? So obviously I could create a hash function which is not random, where I basically take, if I said if true, return 1, then that would be a terrible hash function. But it's fairly obvious from that I've constructed a hash function that makes no sense, right? I'm basically disregarding all of my entropy. Whereas you can look at, because all hash functions are really just mathematical operations, you can look at that hash function and say, okay, when I'm passing this through here, I'm not actually throwing away any entropy, I'm just like redistributing it. As long as I redistribute it in a way that's uniform, then it's fine.
So the randomness that we are looking for, like with the measurement, is for it to be not exactly the same as the previous observation and the next one. Like, its own distribution doesn't matter. Is that true?
Sorry, can you say that again?
So if you wanted to build a quantum random number generator, so would we even care about what the distribution would be that we will like put into the hash function, or do we just want it to be like truly random? Its distribution doesn't matter at all in any way.
Yeah, I mean, so what it really corresponds to in this case is actually what we call a measurement bandwidth, right? So there will be parts of your measurement bandwidth that tail off, right? So if I looked at that entire distribution, I would start to find that things far away from my central bandwidth will be basically very less likely to occur, or I won't see them, right? Or I can get extra noise that aliases into the particular bandwidth that I'm measuring. So what you're really doing is you're talking about flattening out this bandwidth, right? And all measurements have a bandwidth. That's just something that you can't get around. There's no such thing as a perfect detector that measures from 0 hertz through to infinity hertz. You have to at some point define your measurement bandwidth. What you do is you just make it big enough such that in a region that you care about, it's flat enough, right? And so in that sense, you maybe don't care about what the overall distribution is, but you mainly just care about whether it is truly random.
And another thing I wanted to point out, I don't think it's in our agenda, is like how many random numbers you can create. Because my first concern was like when people told me that there is Qrng APIs, I thought they are probably pretty slow. Like they can't generate a lot of random numbers, or it's too expensive. So can you comment on that? I was pretty impressed by the numbers.
Yeah, so we're limited by the fiber connection to servers. So basically, the electronics and the lasers that we have just operate much, much faster than anything. So, you know, the kind of physics that we do, the ultra precise measurement, operates on the time scales of light or atom light and atomic transitions. So we're always going to be limited by actual communication protocols, really. So we can generate numbers, sort of as fast as the detectors can measure them, which can be, upwards of megahertz, depending on what you're measuring. So we can generate, gigabits of data, per second, just from the fact that we're measuring things that are just really, really fast.
So you're basically limited by how fast current detection hardware can detect, pretty much.
Yeah, so that measurement bandwidth that I was talking about is set by the detectors, effectively. So not only the detectors, but the analog to digital converters that those detectors talk to. So whatever those happen to be, that they'll be the bottleneck, because the light is just going to measure as quick as it wants, right? It's I think it's running at 1064, so 1064 nanometers, somewhere in the terahertz bandwidth, but you're never going to measure anywhere near that.
So somebody had asked, and this is probably an Aaron question, is there noise in the measurements, and how do you deal with it?
So the biggest source of noise that you have to compensate for is actually electronic noise. So you just get noise that gets introduced from heat, from just stray particles. Basically, when you're dealing with optical detection, you tend to refer to these kind of noises as either electronic noise, detector noise, and also dark count noise. So that is something we have to compensate for, but you can see if your noise is in the bandwidth that you care about, because it shows up in the statistics of your random numbers, because those are classical noise. So they're not truly random. So if you're not measuring properly, you can actually see it skew the distribution. And
so that's
sorry.
No, goes. I was going to say it's definitely something you can detect, and if it's not random.
Yeah, and so that was the point of measuring those statistics, is if you don't check that this is happening often, if you don't check often, this could happen and you wouldn't know, right? Because to the untrained eye, you have to measure a large enough sum to actually see it. But we can basically see it. But that's the main noise that you have to worry about.
It's another question here. And while I think Burak will probably be answering this one, I'm also going to check the Twitter comments to see if there's any question there, because I've been seeing the YouTube ones here. Is there a way to quantify the trust of first-party oracles, or do you a priori assume it has infinite trustworthiness? I guess it's probably a broad question.
API 3 approaches in general, like it is. Yeah, can you hear me?
Yeah, I can hear you.
Okay, my connection is pretty bad. So yeah, the general approach is that it is quite intractable to quantify the trust of any kind of an oracle. So the API 3 approach to this is, okay, you shouldn't expect the user to be able to quantify this or decide on what to use. So we will just set up these services, but then we will be vouching for them. Essentially, we are quantifying it, and then we are providing a kind of an insurance service on top of them. And then if someone is wrong, we will be wrong, and then we will be paying for being wrong. So it is not the user who needs to be concerned about all that. And then random number generation is a bit different in this regard, because to be able to apply an insurance product, like you would have to be able to retrospectively detect, any kind of problems with the reported data. And then with random number, like if you think about a single sample from a random number generation, you can't tell if it was, actually random or not. You can run like a general statistics over all the reported numbers, and you can show that okay, there haven't been any bias or skew. But then if you think about a single sample, that can be anything, that can be actually random or not. So it essentially doesn't make sense to provide a kind of an insurance product for random number generation, because it is impossible to prove any wrongdoing. So I guess the main point is that you can't provide an RNG service with quantifiable security. So the next best thing that you can do is get that service from the most trustworthy people possible. So that is why we are trying to find a first-party equivalent for random number generation. So ideally, you would use trustworthy random number sources, and then also you would be using multiple of them and aggregate them, which would be the ideal solution. It would still not be quantifiably secure, but then that is, due to the nature of the problem.
And I think we've kind of already established that ANU has a 10-year plus history of providing this to not just anybody who wants to call the API, but like some pretty big names, some academic institutions and stuff like that. So I would wager to say that Aaron has some confidence that it definitely works and does not get tampered with and continues to do what it says it does. Because like he said, there's people at the university that have a personal interest in making sure this works. So I'd like to think it's trustworthy. But that's an Aaron question, is it?
yeah. I mean, for sure, right? I mean, the
It's a matter of...
Sorry. No, Burak must be
Anyway.
dropping out.
So I just have a lot of lag. Go ahead.
Sorry about that.
All good. Yeah, I mean, I think you're always going to have the problem of trust, right? To some degree, especially as Burak pointed out, like, you can't tell if any individual number is random or not. You have to look at a distribution of them. But that's one of the things, is it becomes tricky to try and skew a distribution, especially if you don't know what people are doing with the numbers, right? Like, just because I give you a random number doesn't mean I know what you're going to do with it. I would have to know what you were going to do with it, what decision you were going to make based on that as well, and then skew it in that particular direction. But once again, if I start skewing it, it shows up in the distribution, right? So you can start to do things like, pick times, that are like random times about when you're actually going to sample these numbers, right, and do a dump that you're going to publish. But you can also do things like feedback to the community and say, well, here's a bunch of numbers for you to test as well, right? And so, double checking that everyone's getting the same answer, those kinds of things.
And it's something that's gone through like rigorous testing that, yeah, this is random. Like, so yeah, I think I answered it pretty well. Let's see. I think we had some questions that people had asked kind of pre-call, but these are more kind of API 3 directly related rather than Qrng related. So these are probably going to be for Burak. If Burak is still with us. And he goes off just as I say that. But Aaron, if you'd like to kind of talk a little bit more about, is there anything that you've seen the Qrng or the quantum number API used for so far that is kind of a use case that you can think of? Or something that maybe as you've been talking, you can think, oh, somebody could use quantum numbers for this one.
Yeah, I mean, the big applications that I tend to deal with is in research, not necessarily just physics, but also things to do with healthcare. People really care about randomized trials. They care about being able to sample randomly from distributions, especially when you're looking for really small effects, right? So if you're looking for a very, very tiny effect, then your sampling actually starts to matter. Because if you draw bad samples or from a slightly biased distribution, that can actually really skew your results when you're looking for a very small change. So those are the big ones that we mostly touch. There's been sort of weird cases I know of. We had someone write to us they wanted to know if it was okay to use the Qrng to pick a name for their child, and we said, I guess if you want.
I love it.
We can't stop you.
Right. I love those kind of novel things that, random people will just come up with something that you didn't think of. Like your quantum machine named a child. Like, can you imagine that when you were building it or working on it or testing it or anything like that?
Yeah, no, I certainly didn't imagine that.
I love those novel use cases that show up, though. I mean, we've had APIs that we've onboarded and stuff, and I'm like, how is somebody going to use this? And then people come up with ideas and people use it, and people build projects that I haven't seen. There's a lot of innovation in the space, which always surprises me. So maybe there will be a on-chain baby name generator or something like that uses quantum, baby name NFT generator or something like that. I don't know.
Yeah,
Burak.
some of the more out there things, I think people, they like to they like to connect the quantum thing to being connected to the universe, right? In some fashion, it's like the universe is telling them what to do.
The random particle movement has determined my baby's name. I love that. Seriously, not even making fun of that. I think that's really cool. We got a question in YouTube, which I think is kind of just a general question. When will we see quantum random NFTs? I guess kind of mentioned NFTs a couple times. I guess that's really dependent on who decides to implement this. And I think it's great since it's available on so many chains that you can go do that. I mean, there's a lot of chains that maybe, like we've been talking about gas fees and stuff like that, how expensive it is to develop on them and other things like that. I think the fact that it's available on a lot of chains that maybe aren't as expensive as developing on Ethereum, you can see more of that essentially. So I think that'd be cool. Burak, you got any feedback on the quantum NFTs?
I think I missed a lot of it. My connection is super choppy.
You need the quantum internet connection. The instant internet connection.
Yeah, I mean, quantum NFTs would be kind of a cool thing to see. Like we've generated some artwork that actually hangs up in our office based on the random numbers, just RGB strings that we printed out onto a pretty canvas. But with a lot of the generative AI stuff that you get now, that basically takes noise as an input and then generates something interesting from that, you could actually just have things that are automatically generating art via some generative network that's fed by a quantum random number or series of quantum random numbers, which would be pretty cool.
Yeah, another person had just asked, will this enable dynamic NFTs? And yeah, I think so. If somebody wants to integrate that into their NFT generation, something like that. I've seen a couple NFT projects that change based on API data that they're collecting about the weather or about the price of something. So definitely you could see that happen as well, I think. Burak,
Like
are you with us?
A mood bar for the universe.
Yeah, it's a very fancy digital version of a mood ring.
But
Yeah.
no.
All right, Burak, do you want to input on quantum NFTs?
I mean, yeah, in general, I think quantum NFT is probably some kind of a dynamic NFT. And as you said, there are a lot of dynamic NFT use cases that use now API data, or at least like almost all of them does, I think. So pretty much any API-free service could be used to build dynamic NFTs, and Qrng is not an exception, I think.
I think it's cool. Like, especially you said there's already art that the Qrng has generated in your office that's like hanging up. So there's definitely art applications to this kind of thing, which I think is cool. And we're getting to about an hour now. So that's generally when we end our calls. If anybody's got another question, I don't see any on Twitter, but we've gotten plenty through YouTube today. So I think that's pretty excellent. Dr. Tranter, thank you for coming in and talking with our community about this. I learned a lot. I mean, I think quantum mechanics and stuff like that is super cool. So I've been very happy to be on this call learning. And Burak has also been on the call. Thank you, Burak, for coming on the call. And there will be another community call coming up soon. We're going to be doing a lot of stuff about QRNG, so there's probably going to be another opportunity to engage and talk about QRNG. Maybe not with you, Aaron, but maybe with some of our other partners, people that are working with it. And as always, you can ask questions when we post the announcement for the call on Twitter. And if you want to get into using this kind of stuff, you can get on Discord and talk to anyone. Oh, we got one last question. I think we can ask maybe one last question here. Something about probabilistic payments for stuff like ads on a decentralized social media network that maybe QRNG could be used for. It's something about a social media algorithm. Can you think of a way that quantum random numbers might be applied to a social media algorithm?
I mean, basically, anytime you have a source of entropy that's being used or something that's being picked randomly, you could just replace that with a QRNG to produce unbiased results. So basically, yeah, sure, why not?
Anything that requires anything that it takes a random input, you can definitely get that from. How they suggest feeds or news randomly. I guess if it's something that runs randomly, then you can apply QRNG to it for sure and ensure more random.
So. A lot of those algorithms tend to be more targeted though, right? So I don't necessarily see the explicit use case there for random number generation, but I mean, depends on what kind of algorithm you're running.
Right. Yeah. I mean, and there might be something that comes up that, once a kind of service or development avenue becomes available to people will figure out ways to use it, right? You guys had the QRNG thing running and people could just call it for whatever they wanted. And I'm sure there's tons of calls that were made for uses that were, we've been talking about the baby name thing, but also other stuff as well. So yeah, once a service is made available, I think people are going to use it for a lot of stuff. So yeah. And we were winding down the call a little bit, so I'm going to continue to wind it down. So yeah, we're definitely going to have some more calls about this in the future. And if you want to get your hands on the API 3 QRNG and use it for your own project development or anything like that, feel free to reach out on Discord. I know our people are pretty active on there, and they will come and help you out. The documentation is all online. You can go to our website. This is something that's free for people to use. We want to provide a service that fosters growth in the space. So it's definitely what we're trying to do. Thank you very much again for coming on with us today. And that's going to, yeah, thank you. That's going to be the end of our call. So see y'all whenever we have another call.